Hello everyone, this is lecture 3 on Laplace transforms, and today we are going to talk about the inverse Laplace transform and how to solve or calculate the inverse of Laplace transform of functions. And in particular we are going to deal with these two methods, method of partial fractions and the convolution theorem. We have already done Laplace transform in the previous two lectures. So I'm going to define now what is inverse Laplace transform. So if Laplace of a function ft is f of s, then ft function is called the inverse Laplace transform of fs, and we write that ft is Laplace inverse of fs, where this L inverse is the inverse Laplace transform operator, and such that this operator, when operated on this Laplace, it becomes the identity operator. Okay. So that means if I take Laplace inverse operator on both sides of this equation, then Laplace inverse of Laplace will be identity, so it becomes ft, and here it becomes Laplace inverse of fs, which is our this new definition. And so to calculate uh, inverse Laplace of functions fs, we can use the properties. Okay. Or there are two particular methods which are important here, the method of partial fraction and convolution theorem. This is because we have seen that when we take Laplace of ft function, it ends up on the function of fs, which are polynomial by polynomials. Okay. So if you have using inverse Laplace transform, then the properties that we used for Laplace in the forward direction, we can use the same properties in the backward direction to find result. And in case the polynomial by polynomial are such that the denominators are higher order, or there are product of linear quadratic factors, etc., then we can use method of partial fraction to separate them and again use these properties. And there is a definition convolution. So in Laplace we can use a theorem which is called convolution theorem, which is from the definition convolution. So we'll talk about this also today. So first is that when we studied Laplace, we said that there are elementary functions whose Laplace we need to remember, like Laplace of 1 is 1 by s. Okay. So now I'm saying that if you remember those 7 forward elementary Laplace transforms, then we can just rewrite them backwards to and remember that inverse of those basic elementary transforms. Okay. So to start with, we must remember the Laplace of ft is fs, then ft is Laplace inverse of fs. And I'm going to just rewrite those 7 functions in the forward that we did in the previous lectures, and then just rewrite them in the backward direction so that you can easily remember them and you can use them in both ways, the during Laplace or inverse Laplace. So first result, that elementary result we did, was that Laplace of 1 is 1 by s. Okay, and we proved this also. Now I'm saying that if this is true, then Laplace inverse of 1 by s is 1. Okay, so immediately if you remember this, then you can easily remember that Laplace inverse of 1 by s will be 1. The second result is the Laplace of exponential. Laplace of e power at is 1 over s minus a. So if I operate both sides with Laplace inverse operator, then it immediately gives that Laplace inverse of 1 over s minus a is e power at. Okay. So is the second result. We need to remember that 1 over a linear factor s minus a is nothing but exponential function. Third is that the Laplace of a polynomial t power n is gamma function n plus 1 over s n plus 1. Okay, where if n is integer, then this will numerator will be n factorial. So Laplace inverse of 1 over s n plus 1. Okay, will be t power n gamma of n plus 1. So just dividing this on other side and taking Laplace inverse on this, so we'll get this result. Okay. Fourth and fifth we said sine and cos trigonometric functions. So Laplace of sine 80 is a over s square plus a square. So Laplace inverse of a over s square plus a square will be sine 80 function. Okay. And similarly for cos 80, okay, Laplace of cos 80 is s over s square plus a square. So Laplace inverse of s over s square plus a square is cos of 80. Then we set two results for hyperbolic. So Laplace of sine hyperbolic 80 is a over s square minus a square, and so Laplace inverse of a over s square minus a square is sine hyperbolic 80. And similarly Laplace of cos hyperbolic 80 is s over s square minus a square. So Laplace inverse of s over s square minus a square is cos hyperbolic 80. So I believe that these seven results are already known, in the sense that in the last two lectures we uh, said that we have to remember these seven properties of Laplace. So obviously these inverse properties are well known, or you can remember them easily because of this forward direction result already known. Okay, and so we can easily calculate the Laplace of functions which are directly linked to this uh, elementary functions. Okay. uh, Also in the last two lectures, when we said Laplace transform, then we said that together with these elementary result, if we remember seven elementary properties, then we can combine them to find Laplace of many functions. So now just like we did these results in the backward direction for Laplace inverse, those properties also we can utilize in the backward direction for Laplace inverse. So second thing that we need to remember is the seven properties in the backward direction. Okay, so I'm just putting them here again. So I'm saying that if Laplace of inverse of Fs is Ft and Laplace inverse of Gs is Gt, then the first property that we did is linearity, and so the linearity Laplace inverse of linear combination of or sum of two functions is uh, sum of individual Laplace inverse. Okay, and because Laplace inverse of Fs is Ft and Laplace inverse of Gs is Gt, so we have a result that it is A of Ft plus B of Gt. Okay, so Laplace inverse of sum of function is sum of individual Laplace inverse. Okay, so this one property which was there in Laplace is there for the inverse. Second property is the first shift. Okay, or the S shift. So we said that the Laplace of Ft is Fs, then Laplace of e power at Ft will shift s to s minus a. Okay, so now, so if I operate with Laplace inverse both sides, then Laplace inverse of f of s minus a is e power at Ft, or it is e power at Laplace inverse of Fs. Okay, so first shift, so if you have s minus a, then exponential and Laplace inverse of Fs, which is Ft. Okay, so we can remember this result again. Okay, because we already said that Laplace of e power at Ft is f of s minus a if Laplace of Ft is Fs. Okay, so that result in the backward direction. Okay, so if you remember Laplace result here, this property is again easy to remember. The third property is change of scale. Okay, so Laplace of f of ks. Okay, the scale of s is changed to ks, then its result is 1 by k f of t by k, where this f is Laplace inverse of Fs. Okay, so it is again similar property. uh, Multiplication by s. Okay, so Laplace inverse of s Fs is derivative with t of Ft. Okay, so provided f0 is 0. Okay, so if you remember that Laplace of derivative of function, so then it is s Fs minus f0. Okay, so if f0 is 0, then Laplace of derivative of function becomes sfs, and so Laplace inverse of sfs becomes derivative of function. Okay, so this result. Fifth property, or sorry, in general, this can be extended. So multiplication by polynomial s power n to fs is nth derivative of function, provided the n minus 1 derivatives at 0 are 0. Okay, so this is just extension of this result. Okay, the proof we have already done for the Laplace transform, the same proof, and then you apply Laplace inverse on both sides. Okay. Fifth property, division by s. Okay, so we know division by s means integral. Okay, because the Laplace of integral means division by s. Okay, so 1 by s of fs, its Laplace inverse is 0 to t ft dt. Right, so it can be also generalized. So if I have division by s square, then 1 by s one integral and 1 by s will give another integral. So it will be a double integral 0 to t 0 to t. Okay, so we can extend this also. Sixth property is derivative by s. So Laplace inverse of derivative of fs is minus tft. Okay, so because we know that Laplace of tft multiplying with t means minus derivative, so we just take minus other side and take Laplace inverse on both sides. Okay, and this can be generalized that Laplace inverse of nth derivative of function is minus 1 raised to power n t power n ft. Okay, and 1/7th result is integral of s. Okay, so Laplace inverse of s to infinity fs ds is ft by t. Okay, so we in the Laplace transform we said that Laplace of ft divided by t is this integral s to infinity fs ds. Okay, so Laplace inverse of this will be ftt. So these seven properties. Okay, and if you remember the properties of Laplace transform, then you can just rewrite them into this Laplace inverse transform. So you need not remember them exactly, you just need to remember the properties of Laplace, and for them if you apply Laplace inverse on both sides, they are automatically generated. Okay, now we can utilize them to say solve some example and show you how to do it. Okay, so for example, find the inverse Laplace transform of this fs function, which is s square minus 3s plus 4 by s cube. Okay, so denominator is only s cube, so we can apply linearity here. So s square by s cube is 1 by s minus 3 by s square plus 4 by s cube. We can separate them, and linearity, by linearity we can separate them it as Laplace inverse of this whole is Laplace inverse of first plus Laplace inverse of second plus Laplace inverse of third. Okay, and then we can uh, apply the elementary result for the result. Okay, so its Laplace inverse is simple Laplace inverse of this. Okay, so we can separate them into 3, and then Laplace inverse of sum is sum of Laplace inverse, so we apply linearity here, and then individual Laplace inverse is known. Laplace inverse of 1 by s, we know it is 1. Laplace inverse of 1 by s square, okay, so we know it is t. Okay, and Laplace inverse of 1 by s cube. Okay, so we know that it is t square by 2. Okay, so easily we can calculate the Laplace inverse of this function. So take another example, say Laplace inverse of 1 over s minus 2. Okay, so here we have like in the denominator s, so it is like a division by s. Okay, so 1 by s of 1 by s minus 2. So we can apply the rule of division by s. If we know the Laplace inverse of 1 over s minus 2, then 1 by s division by s property can be applied. And we know the Laplace inverse of 1 by s minus 2. Okay, it is e power at, where a is 2 here, so e power 2t. Okay, so recall that Laplace of 1 by s minus, oh, here it is Laplace inverse. Okay, Laplace inverse of 1 over s minus 2 is e power 2t, and then division by s means integral. Okay, so Laplace inverse of this function, division by s means integral 0 to t of Laplace inverse of fs, rest of the function, which is 1 by s minus 2, and its Laplace inverse is e power 2t. So integral 0 to t e power 2 t dt, and its integral is known, exponential divided by the derivative of exponent, which is 2. Put the limits, upper limit minus lower limit, so we have a result. Okay, one third last example, say find the inverse Laplace transform of s over s plus 3 square plus 4. Okay, so if you this 3 is not here, it is s over s square plus 4, which is cosine. Okay, Laplace inverse of that function is known. So we can shift this, okay, s plus 3 by using first shift. Okay, so if I apply first shift here, then e raised to power minus 3t, and wherever s is, it becomes s minus 3. So if we add plus 3 and minus 3 in the numerator, then we can utilize first shift here. Okay, so Laplace of inverse of this function is e power minus 3t. Okay, so we applied first shift. Okay, so s plus 3 becomes s, and so because s plus 3 becomes s, this becomes s minus 3. Okay, so s minus 3 over s square plus 4, and this we can separate as s over s square plus 4 plus minus 3 over s square plus 4, and then apply linearity to separate into two Laplace inverse. And Laplace inverse of this is known, it is cos of 2t, and Laplace of this inverse of this will be, if I multiply and divide with 2, so 2 over s square plus 4 Laplace inverse is sine 2t, so it will come minus 3 by 2 sine 2t. Okay, so Laplace inverse of this very simple function is again easy to calculate. Okay, uh, but now if the denominator functions are more complex polynomials, complex means here this function is s minus 1, this is s minus 2. Okay, so then we cannot just apply this, but if we use the method of partial fraction, then we can separate them, apply linearity, and then we can solve it easily. Okay, so this method of partial fraction, which says that if fraction of form this polynomial by polynomial where m and n are positive integer is called a rational algebraic function. Okay, and so if we have to find the Laplace inverse of this function, we just need to rewrite the denominator into product of linear and quadratic factors, and then use partial fraction to separate them, and then we can use Laplace inverse linearity property, because Laplace inverse of sum will be sum of individual Laplace inverse. Okay, so what we have to do is we have to resolve this by partial fraction, and for that we first factorize the denominator into real factors. These will be either linear or quadratic factors, and some of the factors may be repeated, like if you have s minus 1, then it can be s minus 1 whole square, s minus 1 whole cube, and so on. Okay, so if you have a linear factor which is non-repeated, means that order is 1, then the corresponding partial fraction will be a over s minus a. Okay, so for a linear factor of form s minus a, corresponding partial fraction is a over s minus a. Okay, so this one, if this linear factor has a power of say r, then this corresponding fraction will be sum of factors. Okay, so I'll put this here. For a linear factor of form s minus a power r, the corresponding partial fraction is this. Okay, constant over s minus a, okay, with power 1, plus constant over s minus a power 2, plus constant over s minus a power 3, plus so on, constant over s minus a power r, where this r is the power here. Okay, so similarly, this for linear factor, if you have a quadratic factor, okay, so if you have a quadratic factor of form s square plus as plus b with power 1, then the corresponding partial fraction is as plus b over s square plus as plus b. Okay, so as plus a linear factor in the numerator. Okay, so if we have a linear factor, we have only a constant in the numerator. If we have a quadratic factor, then we have a linear factor in the numerator. Okay, and if this has a power of r, then just like we did r times this sum, then this also has to be written r times with one power, second power, third power, and so on. Okay, so if s square plus as plus b is power r is a it's a quadratic factor, not a linear factor here, quadratic factor, then the corresponding partial fraction is a linear factor divided by this quadratic, plus another linear factor divided by quadratic square, plus another linear factor divided by quadratic cube, and so on up to denominator quadratic power r, where r is the same. Okay, and then we have to solve both sides and find these constants, and once we have these constants, then we can take Laplace inverse of this sum as sum of Laplace inverse. So we can apply linearity, and once we apply linearity, then this is we can solve Laplace inverse of say this using one of the properties along with elementary result. Okay, so take say for example, find the inverse Laplace transform of this function 2s square minus 6s plus 5 over s cube minus 6s square plus 11s minus 6. Okay, so Laplace inverse of this directly by any property or elementary result is not known because the power denominator is a polynomial which is cubic. Okay, but we resolve this into linear quadratic factor and use partial fraction, then we can separate it. Okay, so I'll just do it. Okay, so the denominator can be written as product of s minus 1, s minus 2, s minus 3. Okay, and so all the factors are linear and of power 1. Okay, so it's the case 1 in partial fraction. So if we resolve this into partial fraction, so the s minus 1 factor can be written as a over s minus 1. Okay, constant by s minus 1. Similarly, the s minus 2 factor is also of power 1, so it can be written as a constant by s minus 2. And s minus 3 also a factor of power 1, so it can also be written as a constant by s minus 3. Okay, and then we just need to calculate these a b c, so that then we can apply Laplace inverse on both sides of this to calculate the Laplace inverse of original function. Okay, so for to calculate a, if I multiply both sides with s minus 1, okay, so this s minus 1 will cancel out here and it will be a, and this whole function will part will be multiplied with a s minus 1, and on this side s minus 1 will cancel out. Okay, and then if I put s is equal to 1, so if I multiply both sides with s minus 1 and put s is equal to 1, then this factor will become 0 because it is multiplied with s minus 1. Okay, so if we put s equal to 1, this factor will be 0. This will be a because s minus 1 is already cancelled out, and here s minus 1 is cancelled out, and rest of the factor if I put as s is equal to 1, then I will have a value. So a value will be put s is equal to 1 here. Okay, this is cancelled out, so 2 minus 6 plus 5, so 7 minus 6 1, and minus 1 minus 2 is plus 2. Okay, so 1 by 2 will be the value of a. Okay, similarly, if I have to calculate b, that means I multiply both sides with s minus 2 and put s equal to 2. Okay, so if I multiply this with s minus 2 and put s equal to 2, this will become 0. Similarly, if I multiply this with s minus 2 and put s equal to 2, this will be 0. So multiplying this with s minus 2 and put s equal to 2, it will be b. So right hand side will become b, and on the left hand side multiply with s minus 2, so s minus 2 will cancel out, and then put s is equal to 2 means in the remaining I have to put s is equal to 2. Okay, so if I put s is equal to 2 here, it will be 8 plus 5 minus 12. Okay, so it will be 1, and 2 minus 1 1, and 2 minus 3 is minus 1, so it will be 1 over minus 1, so b value will be minus 1. Similarly for c, you multiply with s minus 3 and put s is equal to 3, so these two terms will be 0 and it will become c on the right hand side, and on the left hand side I just need to put s as 3 in this. Okay, so in this way I can calculate a b c easily. Okay, half minus 1 and c 5 by 2. Okay, so if you put c s as 3, okay, so 9 plus 2 18, or sorry 9 times 2 18 plus 5 23 minus 5, oh, what I say, okay, so put 18 plus 5 23, and minus 18, so 5, and 3 minus 1 2, and 3 minus 2 1. Okay, so 2 5 by 2. So take Laplace inverse on both sides of this. Okay, and put a b c value. Okay, so Laplace inverse of left hand side is Laplace inverse of right hand side, where a b and c is substituted as half minus 1 and 5 by 2. Then now I can apply linearity here. Laplace inverse of this sum is sum of individual Laplace inverse. Okay, and Laplace inverse of this is known. Okay, 1 over s minus 1 is nothing but e power t. Laplace inverse of 1 by s minus 2 is known, e power 2t, and Laplace inverse of 1 over s minus 3 is known, e power 3t. Okay, so we easily has a result here. Okay, so we can use partial fraction, and then we can use properties to find the result. So I take one more example here. Say find the inverse Laplace transform of 4s plus 5 over s minus 1 whole square s plus 2. Okay. So again now we can use first the partial fraction, and for partial fraction s minus 1 has a power of 2, so it will be give two factors, a constant over s minus 1 plus another constant over s minus 1 square. Okay, so because it's of the form s minus a power r. Okay, and s plus 2 has a power 1, so it will give only one linear factor c over s plus 2. And then we can calculate different constants. For c I multiply both sides with s plus 2 and then put s as minus 2. Okay, for b I multiply both sides with s minus 1 whole square. Okay, and then put s value 1. And for a this is not possible by just multiplying s minus 1 and putting s equal to 1, because this will be b over s minus 1 which will shoot up. Okay, so in that case for this factor you have to put some different values, say s is equal to 0 on both sides, and because b and c are already calculated we can calculate a. Okay, so on solving this for a b c, a is 1 by 3, b is 3, c is minus 1 by 3. Okay, so it's easy to solve, or you can take LCM on right hand side and then denominator will cancel out, and then you'd use three different s values to find three equations and solve for abc. Okay, that can be done. Okay, so put ABC value back here, take Laplace inverse on both sides. Okay, so Laplace inverse of left hand side is Laplace inverse of right hand side, and here now we can use linearity to separate them. And Laplace inverse of this is known, e power t. Laplace inverse of this, okay, so by first shift it is e power t times Laplace inverse of 1 by s square, and Laplace inverse of 1 by s square is t, so it's this quantity Laplace inverse is t times e power t. Okay, and Laplace inverse of this is e power minus 2t. Okay, so these three result easy to calculate. Okay, so I take one more example here with one of the factor as quadratic and other as linear. So again we take a partial fraction to separate them. For the linear factor s minus 3 with power 1, there is only constant by s minus 3, and for a quadratic factor we said linear divided by quadratic, so bs plus c over s square plus 4, and then we have to calculate abc. Okay, so as we said, for this multiply both sides with s minus 3 and put s is equal to 3, we will get the result, so it will be 3 over 13. Okay, and similarly we can take LCM, and we can put different s value to find b and c also. So on solving this we'll get a value, b value and c value, substitute them back here, and then take Laplace inverse on both sides. Okay, so Laplace inverse of left hand side is Laplace inverse of this right hand side, and then we can resolve this using linearity, Laplace inverse of this plus Laplace inverse of second plus Laplace inverse of third. Okay, so this can be rewritten using linearity property, and then Laplace inverse of this is known by property e power 3t. This is a Laplace inverse of this is cosine function, and Laplace of this is a sine function. Okay, so cos of 2t, and for this sine of 2t, but that for that we have to multiply and divide by 2. So multiply by 2 here, divide by 2, so it will become 2 by 13 and sine of 2t. Okay, so we have a result again. Okay, so this is how we can calculate using the partial fraction method. The third is the use of convolution. Okay, so by convolution is the definition here. The convolution of two functions f and g is written as f star g, and is defined as the integral of the product of two functions after one is reversed and shifted, so that we can write this as an integral. So f star g of t means convolution of f and g function, and it is defined as the integral of product of these two functions f and g, such that one of the function is reversed and shifted. So I have rewritten g here, gt function as reversed and shifted. So in terms of gu it is, so reversed means gu becomes g of minus u and then shifted by amount of t, so g of t minus u. Okay, so here I said that one of the function is reversed and shifted, so I have written g as a reversed and shifted, but you can also use the f as reversed and shifted. Okay, so I can also write this integral as g of u multiplied with f of t minus u du. Okay, so either way it is true. Okay, then this result can be utilized to find the Laplace inverse of functions. Okay, because of this convolution theorem, which says that if you know the Laplace inverse of fs as ft and Laplace inverse of gs as gt, then the Laplace inverse of product of fs and gs, where this product is a simple product, it is not convolution. Okay, it is just fs multiplied with this gs. Okay, fs is a function, gs is a function, just their product. The Laplace inverse of product of two function fs and gs is nothing but the convolution of f and g, where these f and g are Laplace inverse of these fs and gs. Okay, and because it is convolution, so that means it can be calculated using this integral f of u g of t minus u du. Okay, or f of t minus u gu du. Okay, either way it gives the same value. So we'll prove this result that if Laplace inverse of fs is ft, Laplace inverse of gs is gt, then the Laplace inverse of product of function is nothing but convolution of functions. Okay, so to prove this, let this integral be equal to some phi function. So let phi t be this integral 0 to t f u g t minus u du, and then we'll prove that Laplace of this function is fsgs product. Okay, Laplace of this, because if I operate on both sides with Laplace, then this will be fsgs and equal to Laplace of integral. So we'll just prove that the Laplace of this integral is fsgs, and then inverse operator immediately gives this result. Okay, so we take the Laplace on both sides of this. So Laplace of phi t equal to Laplace of this. Okay, and by definition, Laplace of any function is integral 0 to infinity e power minus st of that function, and that function here is this integral dt. Okay, so I can just rewrite exponential inside to write this as a double integral. Okay, and then we will draw the double integral into ut plane. Okay, so this is the double integral. So Laplace of phi t is this double integral e raised to power minus st f u g t minus u du dt. Okay, so we have just drawn it here. Okay, so this is the region of integration. You can check that is the t and u plane. In limits of u are 0 to t, so that means u varies from u0 to u equal to t line. So u is equal to 0 is this, and u is equal to t is this line. Okay, so lower limit u0 to ut, and the outer limit is t from 0 to infinity. That means this vertical strip moves from left to right, enters the region of integration at origin and moves up to infinity. So this whole is the region of integration. So what I want to do is I want to change the order of integration of this double integral, and we know how to change the order of integration. This double integral is written using a vertical strip, so we'll use a horizontal strip for this region of integration, and then we will redefine the limit and take dt inside du outside. Okay, so we take a horizontal strip. Okay, so the limits, inner limits will be the lower limit for inner integral will be the value of t here. Okay, at the lower point, so t value on this line is u, and the upper limit will be t value on this end, which is extended up to infinity. So for the inner integral, when dt goes inside, the t limits will be u to infinity, and the outer integral limits depend when we enter the region of integration and leave the region of integration when we move from bottom to top. So when this horizontal strip moves from bottom to downwards upward, then it enters the region at u is equal to 0, and then it continue to hold up to u is equal to infinity because this is extended. Okay, so the outer limits are 0 to infinity and inner limit will become u to infinity on changing the order of integration. Okay, so this function, this dt inside du outside, so order is changed and the t limits becomes u to infinity. Okay, so t value here to t value here, and then this strip when moved from bottom to top, it enters at u0 and keeps on moving in this region up to infinity, so u varies from 0 to infinity. Okay, so I hope you know how to change the order of integration by now. And then because the integral is with respect to t here, so this fu can go outside the inner integral, and this function is written t minus u, so we can also add and subtract u in the exponential just to make it t minus u form. Okay, so we can rewrite this double integral in this form where fu goes outside and this exponential, these two if you combine it is e power minus st. That means I've just added and subtracted a u in the exponential and then taken one exponential part outside because integration is with t, so e power minus s you can go outside. Okay, and now to this inner integral, if I substitute t minus u as a new variable v, okay, then dt will be dv because u is a constant here. Okay, integration is with respect to t for inner integral, and the limits will change on the substitution. So lower limit is t value u, so when t value is u then v becomes 0, so lower limit will become 0, and t value is infinity at upper, so v value will be infinity, so on substitution limit will become 0 to infinity for this inner integral. Okay, so outer integral remains the same, inner integral this becomes e power minus s times v because t minus u is v. It's become g of v, dt is dv, du remains du, and limit changes to 0 to infinity. Okay, so now this inner integral is, if you look at this, then it is nothing but the Laplace of g function. Okay, it is 0 to infinity e power minus sv gv dv. It is Laplace of g function, which we can write as g of s. Okay, g of s, and then because g of s has nothing to do with this integral, it goes outside. Okay, integration is with respect to u, and then this second integral is nothing but the Laplace of f function, so I can write it as fs, and because it's a simple product, so I can write fs into gs. Okay, so Laplace of phi is fsgs. If I take Laplace inverse operator on both sides, so Laplace inverse of fsgs will be phi t, and phi t is, we assumed it to be that integral. Okay, so Laplace inverse of fsgs is phi t, and phi t we assume to be this integral, which by definition is nothing but the convolution of f and g. Okay, so this result we can utilize to find the Laplace inverse of functions when you have to find the Laplace inverse of product of functions such that the individual Laplace inverse of these functions are known. Okay, then we can use the convolution to find. Say I take some example here. Say find the inverse Laplace transform using convolution for this function 1 over s into s square plus 4. Okay, so this function we can solve using properties also because it's a division by s, and for rest of the function we know that it is Laplace inverse is sine. Okay, so it is nothing but Laplace inverse of 2 over s square plus 4 is sine 2t, and then division by s is integration of sine 2t. Okay, but let us see how we can use convolution here. So if I define this function as 1 by s into 1 over s square plus 4, then my fs is 1 by s and gs is 1 by s square plus 4, or you can take gs as 1 by s and fs as 1 by s square plus 4, it is all right. Okay, so I just defined, say, one fs as 1 by s square plus 4 and gs as 1 by s. So I have defined these such that their product is this given function, and their individual Laplace inverse is known to me because Laplace inverse of this fs is a sine function, and Laplace inverse of 1 by s is known to me as 1. Okay, so immediately I have this Laplace inverse of fs is Laplace inverse of 1 by s square plus 4, which is half of sine 2t, and Laplace inverse of gs, which is Laplace inverse of 1 by s is 1. Because Laplace inverse of these are known, so their product Laplace inverse by convolution is a integral 0 to t ft gt. Now this is ft, this is gt, and in convolution one of the function is to be shifted, okay, and reversed, okay. So because this gt is 1, its g of t minus u is also 1, okay. So shifted reverse and reverse function is also same, so it is easy to write here. Laplace inverse of fs into gs is Laplace inverse of this whole function, which by convolution is integral 0 to t f of u, okay. So this ft is written in terms of f of u, half of sine 2u, and g of t minus u. So g of t is 1, so g of t minus u is also 1, okay, constant number, and du, okay. So now this integral is easy, is the integration of sine function, okay. So we can easily integrate, substitute the limits, upper limit minus lower limit, and we have a result, okay. So this one example is very simple. I'll take one more example here. Say find the Laplace inverse transform or using convolution for this function s square over s square plus a square plus into s square plus b square, where a and b are some constants, okay. So again if I have to use convolution, then I have to write this function as product of two functions whose Laplace inverse is known. So if I take one function as s over s square plus a square, its Laplace inverse is cos of at, and the other function as s over s square plus b square, its Laplace inverse will be cos bt, okay. So take fs as this, gs as this, so that fs into gs is this function, okay. Now Laplace inverse of fs is known, cos of at, Laplace inverse of gs is known, cos of bt, okay. So Laplace inverse of product by convolution theorem, okay. Laplace inverse of product means Laplace inverse of this original function is integral 0 to t cos f of u, okay. So f of t is this, so f of u will be cos of au, and g of t minus u, so cos of gt is this, so g of t minus u will be cos of b of t minus u, okay. So this, now we can solve this integral. If I divide and multiply with 2, then I can use 2 cos c cos t formula, and then by linearity we can separate integrals, and we can integrate, okay. So divide with 2, multiply with 2, use 2 cos c cos t formula, okay. And then it is integration of this first cos function plus integration of this second cos function, and we know it is a sine function divided by this, okay. Integration is with respect to u only, okay. So that you need to remember. Substitute the upper limit t, so u value t minus u value 0, okay. So substitute those values, and then we can just take LCM and rewrite this, okay. So we can have a final result. So this elementary result of integration I am skipping here, okay. So take say uh, two examples I have taken on convolution, okay. Now here we have to find the inverse Laplace transform of cot inverse of s plus a by b, okay. So see, we cannot use convolution here, and also we cannot use partial fraction here, and no elementary result of cot inverse is known for Laplace inverse, okay. So how to calculate Laplace inverse of like cot inverse of some function, of log of some function, okay. So can we transform this function to any other function where it this cot inverse will be eliminated and we have a polynomial form, okay. So immediately you can see that if I take the if I assume this as fs is equal to this, and if I take derivative of this, so derivative of this will not have cot inverse, okay. So let fs be this original function, and then here we will utilize this property, okay. The Laplace inverse of fs is ft, then Laplace inverse of derivative of function is minus tft, okay. So this property is known, and if I take the derivative of this, then the right hand side will not have cot inverse, it will become polynomial. Let us take derivative on both sides of this equation with respect to s. So what we have is derivative of s of fs on left hand side, and derivative of cot inverse function, and then you can calculate, and it is minus b over s plus a square plus b square. So you see that the derivative function is a polynomial by polynomial, okay. And we can use now property or partial fraction on this to find its Laplace inverse. So instead of finding the Laplace inverse directly from here, which is difficult to do, we can use the derivative to rewrite this function and then use the Laplace inverse on the derivative. Okay, so if I take inverse Laplace on both sides of this, then the left hand side Laplace transform is minus TFT, and right hand Laplace transform I can use S shift, and then B over S square plus B square will be sine BT. Okay, so on the right hand side, Laplace inverse of this is exponential shift or S shift, which is e power minus AT because of S plus A, and Laplace inverse of this is sine BT, and Laplace inverse of this is minus TFT. Okay, and then I can divide with this minus T to find the FT. FT is Laplace inverse of Fs, which is original function. Okay, so minus TFT will be this right hand side, and so I can calculate ft by dividing with minus t. Okay, so ft is this, and ft is nothing but Laplace inverse of fs. So Laplace inverse of this quote inverse s plus a by b is nothing but this result. Okay, so this can be done for functions for which the inverse is cannot be directly found. Similarly for logarithmic functions, say I take one more example here. Find the Laplace inverse transform of log of s square plus 1 over s into s plus 1. Okay, so we do not have any rule directly, but if I take the derivative of this, then logarithm will go off. Okay, so I can just rewrite this first. Say fs is log of this, and log of m over n is log m minus log n, and denominator is product, so as a sum. And then if I take derivative of this on both sides, so derivative with s of fs will be derivative of this, and derivative of log of s square plus 1 will be 1 over s square plus 1. Similarly for this is 1 by s, and this is 1 by s plus 1. Okay, so immediately derivative on both sides will give me a polynomial on the right hand side, and the Laplace of inverse of this right hand side is easy to calculate. So take Laplace inverse on both sides of this. Okay, so on the left hand side, we already said in the last example it is minus TFT, so this will become minus TFT, and right hand side it is Laplace inverse is cosine function, it is 1, and it is e power minus t. Okay, so you immediately have result. So minus TFT is equal to this right hand side, and then we can calculate FT as by dividing with minus t. So log Laplace inverse of this logarithmic function is nothing but this 1 by t plus e power minus t by t minus 2 cos t by t. Okay, so for this tan inverse, cot inverse, logarithmic such function, we have to make use of some property like taking derivatives and then take inverse Laplace transform. Okay, so this is it to start with the Laplace inverse transform. We already did Laplace, we now did Laplace inverse. Now we'll in the next lecture see how to solve differential equations using Laplace transform. So this is very important that we can directly solve the differential equations whose initial conditions are known using Laplace transform to find the particular results. Okay, have a very good day.